Hey, welcome back. We're at like, I don't know, week 3 or 4 left. Today we're going to do rotational volume, and that's when I have some sort of figure usually on a graph in later years, but right now all they're doing is they're saying, hey, there's this figure rotated around this line. So when I rotate it around this line, what does the figure become? I can't do it fast enough this way. What does it become? This is a cylinder. You're not going to believe me, right? This part right here makes a big circle around the outside. This part right here makes a big circle around the bottom. It's a cylinder. The cylinder would have a height here of this line that's parallel to this axis and a radius of this that's perpendicular to the axis. Okay, so that's rotational volume. Let's actually find this one, and then I'm going to show you a different kind made out of a triangle. Okay, so once again, rotational volume is the volume made when I rotate something around an axis. So it's specifically a 2D shape, a square, a triangle, a circle, I don't care, but I'm going to rotate it over the axis. So what's going to happen is when I rotate it around this axis, I already showed you this physically, but I'm just going to sketch it on the paper. That's not a 6, by the way, it's an arrow. So what happens is this and this go around in a circle, and then it becomes a cylinder. So here's my original shape that I'm rotating, and then this is the cylinder that it creates, which is, I think it's pretty cool. So if I want to find the volume of a cylinder, this height right here is the radius. This right here would be the height. And that just means it's sideways. But like when I showed you this way, I said, no, when I showed you this way, I said that this was the height of the cylinder. It's the same. It's just going this way instead. Same thing, same thing. Okay, so then I can find a different color because this is really light, and we can calculate the volume of this. I should have been doing this out loud, sorry. So volume is area of the base times the height. Area of the base is a circle, so it's pi r squared times the height, which is 3. So pi times 2 squared times 3. 2 squared is 4. 4 times 3 is 12, so this should be 12 pi. And then I forgot to put units on this, so let's call these inches. So this would be cubic inches, or inches cubed. And that's how I do this with rotational symmetry. Let me show you with a triangle next. So this is the basic shape. I want you to take a second and see if you can figure out what this will look like when I spin it, but I'm going to make it and spin it for you in a second. So here's the shape. I just taped it to this thing. It's fine. I didn't realize you could see the tape. So I'm going to rotate it. Ready? Let's see if what you guessed was right. What did you get? Yeah, that's a cone. That's like a little ice cream cone right there. This is why you can take certain shapes and like roll them up and it becomes a hat, you know? It's the same thing. Okay, so let's draw it. So there's my axis that I rotated it around, and then what's going to happen is this point right here is going to make that circle, and then it's going to copy itself over here. So I get a cone. Let me put some numbers on this. So here's our cone. We're going to find the volume of this. So volume is a third of the area of the base times the height. Why did I use a dot here and an X here? I don't know. I fixed it. So it's going to be 1/3 times area of the base is pi r squared. The height is the 7. So 1/3 pi 2 squared times 7. This is not going to be a nice number. I should have thought about that before I did it. 2 squared is 4. 4/3 times 7. 7, 14, 28. So 28/3 pi. Cubic centimeters. 28, 7 times 2 is 14, times 2 again would be 28. Yeah, we're good. What is happening here? Okay, that's rotational solids. Let's do one more thing. Let's talk about cross sections. So cross sections happen when I take any shape. Let's pretend like this is all one shape, okay? Like it's not, because it's a bunch of little things. But a cross section is, if I were to cut it and look at it, it's a rectangle, right? So that's a cross section of this. I would never cut it this way because these are beloved magic cards and I would not be a girlfriend anymore. But if I did, the cross section here might even be a square depending on how tall this is. I'd have to actually measure it, right? But the cross section could be different depending on how I look at it. I could also technically cut it like this. That would be another rectangle. Let's talk about why that's important after I write all that down. Uh-oh. I just said all this while I was paused. So if I have a can of soda or whatever, and I cut it this way, I'm going to get a circle out of it. If I cut it this way, I'm going to get a rectangle out of it. I could get an oval. I could get a triangle if I really tried, I think. Like if I made this over here, it would be a triangle. But that's irrelevant. It's really just matters on the horizontal and vertical cuts is what we really care about. But let me show you why this is important. Okay, I could find the volume of this deck, right? I could find the volume of this. If I were to like spread it out like this, it would be the same volume. Nothing's changed in terms of all the green stuff. Nothing's changed. I could also do this, right? I could like rotate it. Same volume still. Nothing's changed. It's still the same amount of cards, same amount of space that's being taken up by them. I could even technically do this and like it'd be the same, right? I could split them in half. I could twist it. I could whatever. So this guy named Cavaleri actually proved this. So Bonaventura Cavaleri, which I had to look up, 1598 to 1647. This is why they think that math was invented by a bunch of old white dudes. But Cavaleri said, okay, if two shapes have the same height and the same cross section, they have the same. Oops, I meant volume, not area. Hold on. And he didn't have magic cards back at the time, but like it's the same idea, right? I could spread these out this way. It has the same height still. It's still the same from bottom to top. It still has the same cross section. It's a rectangle. These have the same area or same volume as this. It's the same. Let me draw it for you, and then we'll be done. So these two shapes have the exact same dimensions. The cross section will be a 4x2 rectangle, both of them. The height for both of these is 3. These are the same volume. So don't be scared if something's crooked is all I'm trying to tell you. All right, that's it. I will see you next week. Goodbye.